Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is part of the great stuff. This is the AAS Journal Author Series. And I am very happy to have Agnès Bischoff-Kim with us today. Hello, Agnès.
Hi, friends. Frank.
Nah, that's okay. I
already messed it up.
Before I learned how to say it properly. It's all good.
Thank you so much for having me.
Oh yeah, well, it's a really lovely article, and we're going to get to it here very shortly. But Agnès, where are you located at? What's your geolocation?
I'm in Scranton, Pennsylvania,
Scranton?
northeast part of the state.
Awesome. Very good. Very good. Let's see. And it is August 20th, 2024 as we record this. And so summer must be in full swing in Pennsylvania there.
It's actually done.
It's done. Oh no. What's happening?
No, I put away our fan yesterday.
Can I borrow it? Can I borrow it? Because I'm in Phoenix and we're still definitely well above the hundreds. So my fan is not going away yet.
Yeah.
That and the semester starting up soon enough. So when do you start the semester there?
Like Monday, next Monday.
Ooh, okay. Let's see, 22. Yeah, I guess I start in like 10 days or something like that. So yeah.
In the middle of the week, is that?
Something like that. Yeah, we start kind of weird. We start like 2 days before the weekend and stuff.
Yeah.
It's an ASU thing. I have no reason for it. Very good. Let's see. And Agnès, what do you like to do for research?
What I do is I specialize in the modeling for white dwarf asteroseismology.
Cool.
So what has occupied me for the past 2 decades is essentially to find white dwarfs that have oscillations that match what we observe.
Cool. Very
this
cool.
Period by period fitting for white dwarfs.
Nice. And that is going to bring us to this very awesome APJ article. It is open access. It's the open access era, people. You can go grab a copy for free. Go get one. Constraints from parallaxes and average period spacings in the Asteroseismic study of 8 hydrogen atmosphere pulsating white dwarfs. And Agnès, take us away.
So as I've mentioned, I've done a lot of peer-to-peer matching, looking at individual objects, really just trying to find an internal structure that of models such that the periods match the observed star.
Cool.
But what has occupied me probably for the past couple of years, and this paper is, there's not a labeled series, but it's a theme in the past couple of years of my publishing. And that was to take a step back. Can we look at things in a more, it's not quite ensemble asteroseismology, but it's look at things in a little broader way. Okay. So for instance, for this one, I was looking at pure spacings. Okay. And not at a period by period fitting. And most of it is stuff that people have done before. I just took a very systematic approach to it. Good. And introduced a new constraint. And this is where my co-author actually comes in, Keaton. I've worked with him before, but this is an idea that sprung for the two of us in 2015. We had a conversation during a conference. Mm-hmm. And we had been thinking about we have distances now from the Gaia mission, parallaxes to white dwarfs. Mm-hmm. And that's something that we've been like, if you don't use a parallax when you model the white dwarfs as a constraint, the referee will say, did you check about did you check your apparent magnitude? So this was a more systematic approach to that. And gosh.
All good. All good. So we got Gaia, so they're giving us some parallaxes there, and we are using TESS, yeah? This is strictly TESS, or you got some?
Yes. So the basic idea is to maybe I should mentioned the main thing we were after it. When I say constraint from parallax and average period spacings, the constraint that we got is on the envelope mass of the stars.
Okay. Okay.
And for 8 objects, the reason we could only do 8, like in the paper, we looked at 9 hydrogen atmosphere pulsating white dwarfs. We looked at 9 of them that looked promising. A promising DA white dwarf would be, DA is the hydrogen atmosphere. A promising pulsating DA has many periods. And in white dwarf asteroseismology, that's half a dozen. Like that half a dozen, we're already happy when we have that. I know in some fields it's nothing, but for white dwarf asteroseismology, we're happy when we have half a dozen.
Yes.
So they were selected like that, and in particular, we are trying to look for stars that have, is it in the title it says average period spacing. So that's important because if we come back to this idea of not doing a period by period fitting, but rather look at in a more general sense, learn about a star in a more general way, the period spacing is a measure of how compact the object is, essentially.
Okay.
So this is why if we look at period spacing, we can learn about the temperature and mass, because that will determine how compact the white dwarf is. If it's more massive, it's going to be more compact. If it's hotter, it'll be fluffier. Fluffy is a big word for a white dwarf, but
it's a very technical term, but I understand it.
So that helps us place constraints there. And also layer masses, because the envelope, if you had a thicker envelope, that gives the white dwarf a chance of being also a little fluffier.
Okay.
Because the core is just degenerate, like you can't really, it doesn't really affect the size of the white dwarf.
Those would be the carbon oxygen core.
Yeah. So that average period spacing, there's a theoretical, so now I think I'm landing back on the paper, section 2, with this asymptotic theory. So that's a theory. This is, there's a prediction that's well established. It's from Uno et al., 1984, that's equation 1. And this tells us what the period spacing should be, the asymptotic. So that's the asymptotic limit where we have, it essentially works for, if we take a real white dwarf, it essentially works for, or a model that's close to, complex enough to be close to reality. It works for the higher K, and K is the radial order. In most fields, it's called N. Other asteroseismology is called that N.
K, and we'll use K here. It's fine.
Okay, in this paper, it's a K. So this works for the higher periods.
Yes.
And so, but to close the loop on the choice of objects, not only were they selected because we had enough modes, like at least half a dozen, we had to have enough longer period modes.
Okay.
And I'm talking about 800 seconds or more. And that allowed us to get a measured average period spacing, which you can then contrast with the model period spacing, and the code will essentially use equation 1 to calculate the asymptotic period spacing. And if we look at equation 1, we see that that asymptotic period spacing depends on K, and it also depends on L. And azimuthal order is it's the K and L of spherical harmonics. So, and I should mention for white dwarfs that L is either 1 or 2, like we're not expecting any higher order. And so that's what we had for objects, L1 or 2.
Okay, all right.
and this, like I mentioned, this works better for hierarchy. Now, the in the brackets and in integrand, we have this n, and that's a frequency, it's the Brunt-Vasselin frequency. It's really important for G-mode pulsations, which is what we have in white dwarfs. And essentially, this is where the Brunt-Vasselin frequency will be lower if you have a more compact interior. No, it's the opposite. Because, yeah, it's lower in the interior and higher as you go out.
Okay.
But the bottom line is it depends upon the how compact the model is, and so it will also affect the period spacing.
Indeed.
So more compact white dwarfs have smaller period spacings.
Okay. Okay.
The equation below that was actually a suggestion by the referee. We had a very helpful and thorough referee on this paper.
Yay.
And the referee pointed me to the Brassard et al. 91 paper.
Okay.
Where he expressed the Brunt-Vasselin frequency in a way that makes it easier to see the dependence of the Brunt-Vasselin frequency on the composition.
Yes.
Composition comes in with that X, yeah, that's where that comes in. So this brings us to another thing that we learn from the period spacing. As I mentioned, it's related to how compact the object is, so mass and effective temperature. But it's also related to the composition. So I think I'm going to jump around because then I have a section on measuring the spacing. This is where my co-author really came in because that's his thing. So he really helped there. So I'll come back to that.
Okay.
But then where my expertise is 2.3, the dependence on model structure, because I do the modeling.
Let's go there.
And one thing there that was new, I think, in this publication, I'm using a method and a code that it parameterizes the interior. So maybe this is where we can go to figure 5.
5, let's slide
Is
down.
it? Yeah.
Yes, this is the input.
So figure 5 is showing the upper part is showing the composition profiles inside a standard model.
Okay.
And for the carbon and oxygen, since I determined that was in a previous publication, I determined that I showed, we already kind of knew in the field, that the carbon and oxygen core really does not have an influence on that average period spacing.
Okay. Okay.
And it will also, another aspect of the work has to do with the mass radius relationship. That's another part of the piece of the puzzle. It also does not have much influence on that.
Okay.
So I fixed that.
Okay.
And I did kind of what you're not supposed to do. I did not really fix it. I used stellar evolution calculations to have them be physical. So they're mass dependent.
Right. Yes.
But since they don't influence the period spacing and they don't influence the mass radius relationship, which are the two things that we used in this publication, I thought that was the best thing to do. At least we have physical, best we know, carbon oxygen profiles. So that's what the bottom the figure is illustrating. It's the LP code from Argentina, the Alteos, Corsico, that team. They have great models. They're available online. Just really love them.
They're great. They're great. There's a shout out, you guys.
It's a great team too. Great work.
Question on the figure. What are the upper figure? What are the vertical dash lines? What do they mean?
Oh, yes. What did they mean? Yes, so these are the one that's a little past the 1, between 1 and 2. That's the base, how we're defining the base of the helium hydrogen layer.
Got it. Okay.
So I know there's a bit of carbon in there still, but
It's
it's where the
AW.
helium and then the hydrogen just become dominant. And
Yes.
that's one way to define the envelope. So I try to be specific, and I always say hydrogen, helium, or helium, hydrogen envelope.
Okay.
So I'm thinking of envelope in terms of composition. We have a transition from being mostly carbon, oxygen, very degenerate, to helium, hydrogen, less degenerate.
Okay.
That's kind of where we are.
I'm with you.
So that's that limit. And then the other line defines where we transition over from pure helium to having hydrogen.
Hydrogen in it. Okay, good.
So that's the base of the hydrogen layer.
Yes. Okay, I'm with
Loosely
you.
put.
Yep.
So that was an illustration of that, because we are going to see results and tables where we have a 10 to the negative 4. We'll see that in some figures. It will say 10 to the negative 4. MH equals 10 to the negative 4. It's that 4 with a 10 to the, because it's the people often ask about, it's a weird scale on the horizontal scale. It's a mass scale, but it is constructed in this weird way so that it expands the outer layers.
Yes.
Because if we don't do that, so the 1 on this horizontal axis means we are at 0.99 mass-wise.
Right. Okay.
So if I did a pure MR plot, as the bottom one is an MR plot, and that's we have the oxygen just going to the edge of the figure, essentially.
We go through the transition.
So if I had put helium on there and the hydrogen, it'd be all squished on the right side. You would not be able to see it very well.
Yeah, it'd just be almost on top of each other, basically.
Yeah. So we often do that when we do white dwarf, when we try to show white dwarf chemical structures. We always have those 2 plots going on. One that shows the core better, and then one that shows the hydrogen and helium envelope better.
Well,
something that we're very used to.
I'm with you. Good. Okay, so this is input.
Yes, so this is, and then what I was varying in this work was the thickness of the hydrogen layer and the thickness of the helium. So here's something that we can do with the white dwarf evolution code that is not so easy to do with the stellar evolution code. If you're using a stellar evolution code, you can turn some knobs and you can have your hydrogen being stripped away more or less. You can have more thermal pulses.
Right.
I'm not an expert on that side, but there's knobs that they can turn in order to strip away.
A forward or linear knob, let's put it that way. Yes.
So yeah, you can strip, you can modulate how much hydrogen your model has at the end. Can't do anything about the helium. That just follows the physics. And so that's, so one thing, but with WDEC, we can do whatever we want. We can create white dwarfs that have no chance of existing in reality if we want to. I've created some by mistakes. I've created some horrors, and the code still converges. So it's pretty scary.
Big code.
So I always plot my profiles to make sure that it's at least fair. So I have that full freedom. I can put as much hydrogen as I want. I can move that boundary around, and I can move the helium boundary around. So that's this 2 dashed line, full freedom, almost full freedom.
Yes.
So I was able to examine, not just in this work, but in previous work, I was able to examine the role that the thickness of the helium layer has on the pure spacing and on the mass radius relationship. And what I discovered, this is just below its convenient, figure 6. Kind of jumping around. I hope I'm making sense.
Oh, good. Yeah, I'm following.
We'll get to the punchline. We're putting the ingredients together, the average pure spacing and the mass radius relationship. We need both. So this figure was examining how the mass radius relationship changes according to different parameters, and those are the parameters that matter. So obviously temperature will really change how fluffy the star is.
Right.
So big difference between 50,000 K versus 10,000. And by the way, I think it's all on the axis. The horizontal is log of the radius in
yes.
centimeters.
Yes.
And then we got solar mass.
Yes.
So yeah, temperature has a big influence. The hydrogen layer has a significance, statistically significant influence. That's the last panel.
Okay, yes. Uh-huh.
But actually not as much of an influence as the thickness of the hydrogen, of the helium hydrogen envelope.
Yeah, the total envelope.
We see that has more of an effect. And that's something that I don't think had been pointed out before or tried or published. So,
Cool.
or else I didn't find it. So I just tested it and I put it in this paper right here.
Good. Okay.
It felt like something that was important to point out and something that was important for my work because I was trying to see what had the most influence and then study that.
Yes. Okay.
Yeah.
Cool.
So that's I'll come back to that. The mass radius relationship is something that we'll need. So maybe now we can backtrack to the pure spacing.
Sure.
So we talked about the asymptotic, like the theoretical one, like the one that comes from the models.
Yes.
But then we want to, where all of this is really interesting is when we can confront it against measurements. So what measure as many of these as we can, and we did 8, which was okay. That's everything I could find. There might be more, but that's all I could find. So that's where my co-author comes in. So he did section 2.2, measuring the asymptotic pure spacing. I am going to give another shout out to Keaton here. He maintains GitHub repositories. He's got associated blogs, and the code and tools that I use for this paper are all there.
Okay.
So actually, I pulled him in. He pointed me to those tools. He taught me how to do this. But after that, I was able to edit his code. It's all Python. It's great, fantastic tools. Like I know students who are using them. Very, very nice resource. And there's a lot more that he does. He's great.
We'll put a link to that repo in the description.
Yeah. I have the link in the paper, I think, but it definitely
we'll put it in the description. Yep.
Yes. So he implemented in his Python routine a number of statistical tools that we have that allow us to find regular patterns in a list of numbers. So this figure 1 and 2, and that's all I had in the paper initially, but the referee insisted that I put all of them. And so the rest of them are in the appendix.
One of 4 appendices.
The appendices below.
Okay.
So the figure 1 and 2 is an illustration for a couple objects.
Figure 1.
And the top 3 panels are different statistical tests and the results that they give. And what they allow us to do is they will detect if you feed a list of numbers to the statistical tests. They will find if there's any regular spacing.
Okay.
And then there will be a peak at that regular spacing. And I've grayed out some regions.
Yes.
Because it can be messy. You get lots of peaks. Some of them are really just emerging. So for some of those objects, there's very little doubt that there's something there. But I grayed out the grayed out areas are from the grids of models. So I run grids of models. And for every model in the grid, so I've I don't think I've said this, but they're parameterized models. So the things I've mentioned, like the thickness of the hydrogen layer, the thickness of the hydrogen envelope layer, the hydrogen helium layer.
Yep.
I'm not going to list all of them. They're in the paper. The top of my head, I don't know if they're even in a table. They got to be maybe in the appendix.
Probably that one has a few tables in it, but
I think I gave a reference for that. Total of 15 parameters right now in WDEC that I can vary, but I went through all the work to see which ones do matter, and that's just the mass matter, the temperature matters, and the thickness of the hydrogen and helium masses.
Nice and physical parameters.
That's it.
Nice and physical parameters, right?
Yeah. And the other parameters, like the parameters that describe the oxygen profile, don't really matter for this work. So like I said, I fixed that.
Fair enough.
So now I have those grids with those parameters that I varied. And for every model, I'm able to compute an average pure spacing.
Okay.
And now I get a range within my grids. There are pairs that never occur. Just DAVs don't do that, like unless they were
Ooh, that's a little short.
extremely low mass, or
Right.
they just
ELMs.
yeah, ELMs, or unless they are of temperatures that are outside the pulsating strips or
Fair.
outside of the ZZ-SETI instability strip.
Fair.
So
Okay.
for the models of interest, we'll call it, there's a range of average pairs that we get. So there's two bands there because there's the L = 2 modes. That's the one at the lower, like between 20 and 28
Gotcha. L = 1, L = 2.
seconds of spacing. That's the L = 2. And then around 40 seconds, that's the L = 1 spacing.
Okay.
So I'm expecting, like, if we have peaks in those areas, we can attribute that to having an L = 1 sequence of modes or an L = 2 sequence of modes. It's a little bit more complicated than that, because you will notice that in both figure 1 and 2, I've highlighted, figure 1 is probably cleaner. It's got those two very clear peaks. One of them is squarely in the L = 1 pure spacing, but then there's this other bump that you can't really ignore.
No, you can't.
That's happening at a little higher pure spacing.
Right.
These statistical tests also pick up harmonics.
Ah, okay.
So if you got 48, that could be 2 × 24 seconds.
Yes.
So maybe that's an L = 2 spacing of 24 seconds.
Harmonic. Okay. I'm with
So
you.
it's an indication. So something that we considered, and then you go back and you look at the star and see whether that makes sense or not.
Okay, good. I'm with you.
So that's the measurements, and this is all courtesy of my co-author.
Very nice.
All right, so I think I've so table 1 lists the results.
Table 1, period spacing
3, 6, 9. So you notice in table 1 we've got 9 DAVs.
Yes, we do. 9.
And one of says non found. We tried. G3829 has lots of modes. It's a star I like. I've been trying to decode it for some time, but it's just a huge mess. It's that pulsating whatever is a terrible mess.
Another attempt here. Okay.
And yeah, another failed attempt, in other words. Yeah. So that we kind of had to, didn't have anything there. But for all of the other ones, we have pure spacing. And I should also point out that people have worked on these stars. So for some of them, there were no prior results, but for a lot of them, there were. Some of these are really old friends.
Yes.
So I also pulled that. Like, if I also pulled some older results in that table as well.
Good.
So that's what we're working with. We've got L = 1 pure spacing for all 8, except for G3829. And then for some of the 8 ones, we also have an L = 2.
Yeah,
that's nice to have. If you have 2 of them, they get more constraints.
Absolutely. Okay.
So that's the period spacing.
20-ish. Okay.
Section 3 is very short. It talks about the constraints from spectroscopy and parallaxes.
Okay.
So that's very short, partly because I presented a method in a previous publication. So that's another refer to another publication. But it's all Astro 101. Again, it's one of these things where I felt the need to write it up because I couldn't find a write-up elsewhere, but it's really just Astro 101. So it's essentially trying to get just once you have a parallax, you have a distance. And once you have a distance, you have a luminosity.
Yes, luminosity distance.
But you also have you have a radius. It's mixed in. It's the Stefan Boltzmann law has both. So if you want to fully define, like we need one more constraint in order to get a luminosity and a radius out of that.
Okay.
And that's where the mass radius relationship comes in.
Cool.
And I also use log G's. I know this is where the spectroscopy comes in as well, because you get the log G from spectroscopy.
In fact, let's take a peek at that. As long as we're talking about it, let's go down to here. Let's talk about this mass radius.
There we go. So this is how I. It's a fit. It's a polynomial fit to third order to the log R, and the coefficients are temperature dependent, because we saw in figure. There was a figure. It was figure 6.
Showing the sensitivities of the different modes.
Yeah, and we saw that the temperature is the greatest influence, so that had to be folded in.
Okay.
But then those coefficients are also kind of considering different, because I think I have a big table under there where I'm listing the coefficients.
4 different envelope masses and hydrogen masses.
4 different. So see, this is a multi. So it's taking all of the influences that we have in figure 6. It's accounting for temperature dependence. It's accounting for the envelope masses as well. So that's why we have all the sets of parameters. So one could just use that table and this equation and just construct any mass radius relationship that's based on the White Dwarf evolution code. And we're getting similar results from other codes. Like, it's not terribly different, but
I mean, that's a pretty good match, 1%.
Yeah.
For that triple or cubic polynomial. Very cool. Good.
Yeah, the 1% is the match to the model. The actual numbers from the grid.
Yes. Understood.
So
okay.
Yeah. So we need. So then you put the parallax and the mass radius relationship together. What does that help us do? So this is where we get to the grand results.
Okay.
Figure 7 and subsequent figures.
Figure 7. Let's take a look at figure 7.
So we can just take one, and we'll have to take it piece by piece. I struggle so much with those figures.
Yeah, a lot of lines.
In the end, like my co-author almost did not let me. Like he said, you got to make this cleaner somehow, and I just told him, I tried, and I just don't know.
Let's just walk through. Let's just walk.
Go ahead. So they're in there.
Let's just describe all the lines. Okay.
So maybe it's best if we focus on one, like take the solid black line.
Solid black line.
These are the easiest to spot. Solid black line.
Yes.
Because we have 2 solid black lines. And they cross.
Oh, right.
Almost at right angle.
Right here. Yes.
Which is very convenient. So the solid black line that is more curved and is slanting, has negative slope.
Okay.
That one is a line of constant period in the grids. So I have at each point in this plot, there is a model. Like, I have a grid of models for different masses, different temperatures, and they're populating this whole plane.
Right.
And for each of those, I'm able. Then I looked for, this is for the L = 1, 40-second spacing.
Yes.
So I picked out, it's a little more sophisticated than that, but essentially I picked out models that had a 40-second spacing.
Yes, it's a 40-second contour from
42, yeah. And furthermore, I picked out the models, that's in the legend. I picked out the models that had an envelope mass of -2.2.
Okay.
So in figure 5, that was that first dashed line that we saw, is the base of the helium hydrogen layer.
Right. Yes. I'm with you.
And then the helium, the hydrogen layer, that was the second dashed line, is at 10 to the -4.5.
Yes. Okay.
So I limited to these models, and then I picked out the ones that had a 42-second spacing.
Okay. Yeah, I can see.
And they're along that line.
Okay.
So that's how that line is constructed. The other line that has a positive slope, this is the one that I get when I combine the parallax, the distance and the mass radius relationship and use some basic physics.
Okay.
And I arrive at a relationship between mass and effective temperature.
I'm with you. Yes.
Yeah.
Okay.
And again, that's outlined in another paper that I do refer to here.
Mm-hmm.
It's not a tough process at all. It's Astro 101. So yeah, we get those two lines.
Okay.
And we're really looking for them to cross.
Yeah.
Because that tells us that we have an agreement, because they tell us a mass effective temperature. Where they cross, we think, okay, that's the correct mass and effective temperature for that object. That's the idea. That was the idea that we had with Keaton.
Okay.
And at the end, I think we'll discuss. We're going to take that somewhere. Like this is like the first go at this, cool. Essentially.
Good. We'll come back to that. We'll come back to that. Okay.
So we have lots of sets of lines here, and then we have also this dot with a box around it.
Yes.
That's the spectroscopy.
Okay. Okay.
Because we're getting to come back to the lines, we can try many different types of layers. Yes. For the envelope and for the hydrogen.
Yes.
Layer.
Uh-huh.
So that's what. So we get many possible solutions. Like whenever same lines cross, we have a solution. Which one is the right one? That's what the spectroscopy box hopefully tells us. Whenever we have lines that cross the spectroscopic box, we have agreement between two different measures.
Okay, I'm with you.
So I would say the negative slope lines would be like from the asteroseismology. That's the average period spacing measure. Yes. And then we get the box is the spectroscopy measure.
So is the size of the box a measure of the uncertainty in the measurement, or?
Yeah, it's the error bars.
Error bar. Okay.
Yeah, error bars. Okay. The 1 sigma error bars.
Okay. Good.
Oh, and I should mention further. This is something that I borrowed again from papers from Alteos and Corsico that we mentioned. We follow each other and we borrow ideas from each other's papers. And one thing that I've seen them do, which I use here because it solved a problem, for those, especially for old timers, like EC14012, GD1212, G2938, those are old friends. Mm-hmm. And we have multiple spectroscopic measurements for these objects. They've been looked at over the years with different models, different groups. And so they each have a measurement with their 1 sigma error bars. Uh-huh. And they don't agree. And so what I used to do is I would put every different box there. But what they do is they just take an average of all of those measurements.
Right, a representative box. Mm-hmm.
And I thought that was a very good idea. So this is an average of all the measurements available for the object.
Cool. Okay. Yeah, that helps declutter a bit.
Yeah.
Quite a bit. Okay.
Yes, it does. So we have this single representative spectroscopic measurement for each object. Okay. And so I was hoping for this to work. So what we're looking for is to have the two lines to cross inside the spectrum.
Inside the box.
Inside the box. That, we solve the star if we can do that. And we don't, like for most of them.
Yeah, I was going to say.
Yeah, I think there was one maybe where it worked a little better. None. Well, maybe for GD1212, we have a cross between the black lines in the corner of the spectroscopic box. We have a cross right there. So overall, we see that there's problems. Right. But I still took away two main conclusions from this. Okay. One is that, one goal was to learn about the thickness of the hydrogen and helium layers.
Yes.
We can discard some.
Okay.
The green, the blue, that's never even close to a spectroscopic box.
Right. Right.
And those are the thinner layers. For the 8 that we studied, they're just not the right result. And this is consistent with extensive work that's been done before, where from stellar evolution,
Mhm.
and also from seismology from other groups of white dwarfs, we agree that more likely white dwarfs have those thicker layer masses rather than thin.
Okay.
They don't all do, but
Singles.
there
Yes.
has been signs, and this is an additional sign that we have here.
Cool.
So that's one thing we can draw from here. And then something that needs to be solved, I think for, well, not all of them, but for a lot of them, we have I call them the Gaia lines, like the positive slope lines that we get from the parallax
Oh, yeah.
and mass
Okay.
radius relationship. By and large, they tend to be at lower temperatures. Well, not in this plot, but I think in the second set in figure 8, we can see.
Okay.
So that's 3 for 3 of the GAVs.
Oh, yeah.
It's also true for EC14 and 12, also true for GD. So I think for 6 of the 8,
Yeah.
the spectroscopy is showing a hotter temperature than the parallax does.
Yes. Mm-hmm. Mm-hmm.
So that's a theme from this work.
Okay. Systematic, let's call it.
This is systematic. I did find a work much more statistically significant. I think it was, I can't find it right now, but there was a paper where they used different methods. So they were not confined to pulsating white dwarfs. They just looked at all of them. And Gaia's got like 200,000 of them or something. It's a ridiculous number.
Yeah.
And in their paper, using different methods, they show the same thing.
Okay.
For their tens of thousands of or more objects. So it's something that they note as well, with many, many more objects than I did.
Cool.
So I think there's something there probably going on.
Okay. All right. Very good. Very good.
I think after that I took star by star kind of.
Yeah, then we sort of walked through each of the idiosyncrasies of each.
I honestly forgot what they were.
Okay, it's all good.
What I was doing is mainly voicing the results that we can see from the figures. So what layer masses do we have? G2938 is interesting because it's got a debris disk around it, like a known one.
Ooh, well, that makes it way more interesting. Okay.
Yeah. So here I was. I looked at of course, if it has a debris disk, that will affect how bright it looks to us.
Right.
And so then the Gaia lines would be shifted accordingly.
Yes.
But I looked at that effect and it goes in the opposite direction.
Oh no.
So the debris disk is not an explanation for G2938.
Okay.
And then the other stars don't have known debris disks.
Good. Very good. Cool. Very cool. Yeah. Very nice. Okay. So
yeah, I do discuss each in turn. Talk about, like I said, these are not like other groups have looked, those are old friends. So in those each of those sections I'm mentioning older results and whether we agree or not.
Good. Okay.
Yeah.
Yes, envelope masses is a theme here. Cool.
Yeah, in the conclusion, there's nothing new compared to what I said. There's just the link to the WDEC, the White Dwarf Evolution Code, is on GitHub.
Yes. Okay.
And then all the tools from Keaton, and he's got more repositories. Like I know he's on GitHub.
Cool. We'll put those in the description below the video.
Yeah.
And then there's 4 appendices of some pretty data.
So I put appendices. This is partly for me myself, like if I want to reproduce that work or take it further, and for others, so that they can know which numbers I used. So I compiled a lot of his compilation. The periods, I compiled the lists, and I'm saying where I got all those periods.
Good.
The spectroscopy as well. I compiled a full list of measurements. So yeah, in table in that table, you can see like for, oh, no, it should be. So
Yeah,
if you read this vertically, you can see how many measurements we have for each stars, and G2938 is just really interesting to people because so many groups have a measurement for it.
Oh, everybody's
So when
doing
I was
it.
talking about averaging out
Oh, wow.
the measurements, that those are the ones that I averaged out.
Wow. Okay.
Yeah.
Wow. Kind of all over on the mass on this one. Anywhere from 0.59 to 0.85. Oh, okay.
Yeah, when you put in individual spectroscopy boxes in the mass effective temperature plane, it's really terrible.
I
The
get
the
your
more
point
one
now,
has
right?
been
Right.
looked
Because
at, the more
they're over,
measurements
they're
you
up,
have.
they're down. Yes.
Yeah, it's that was something that I've been
Yeah.
ever since I started doing that with my PhDs. For my dissertation, I thought, can someone just give me a plus or minus 200 degree
Exactly.
Kelvin? For
Approximately.
sure. Like I want just one measurement. That's correct. Like, no, that
Yeah. Very cool.
doesn't exist.
Very cool.
And then there's more of the pure spacing diagrams. They're kind of they're cool to look at. You can see some of them, it worked really well. So G3829 is the one we had to drop. That's
Right.
figure 11.
Nothing there.
And you can see why we had to drop it. Like
Yeah,
there's nothing.
nothing there.
Yeah.
Nothing there on that one. Bummer. Okay.
Yeah.
Okay. Very cool. Very nice. Honest, I want to thank you so much for walking us through your very lovely article. Thanks. And you kind of touched on it a couple of times, so let me go ahead and push on it a little bit. Where do you think we go from here, given the published article? Is there chances of getting more than 8? Let's say 80. Could one do the same thing with helium white dwarfs? Are there other telescopes going up or other new data coming down that could be applied to? And just sort of, where do we go from here?
So there's several aspects. The helium atmosphere, for sure, we want to use that. My fear there is that there's I probably mentioned that in the beginning. The DAs, pulsating DAs, we've got 500 pulsating. Yeah, I found it. It's interesting. We got we have 500 known pulsating DAs. Okay. And I think it's 50 for dB for the helium atmosphere. So yes. 10 times fewer of them. Okay. So we'll find 0.8 of them. Cool. No, we already know of one. And no, actually, I know of 2 personally that I've studied. So I think we can find more helium atmospheres that would be suitable for this kind of study. Okay. We have not mined all of the test data, K2. Definitely there's work there. Okay. That we could find more objects. And then on the statistical end of things, in terms of being more rigorous with the mass radius relationship, just doing this kind of work, but in a more statistically, in a better way, like stronger. That's essentially, that's one thing that we can do. And that's one thing that my co-author and I are going to be working with over the next 3 years. We just had an approved NSF grant. Oh, very good. Congratulations. So there's a chance that we'll get done. We get the NSF grant. But no, Keaton definitely has more tools, more ideas. He's an expert at statistics. So there's definitely a lot that we are planning on doing with this. How about something like Plato or something along those lines? So follow-ons to tests, I guess, is where I'm looking. Are there other missions going up that might be useful? I have not. I'm still with TESS. Like I have not looked at the next mission. Okay, all good. But eventually there will be one. Yeah. Alrighty. Yeah, very cool. Okay, good. That's been lovely. Honestly, I want to thank you so much once again for walking us through your very lovely article. And that will do, everyone. And I hope this made your pulsational astronomy day just a little bit better. And we will see you on the next one. Bye-bye.